GIS Fundamentals, Section 11, Terrain Analysis. Digital elevation models, DEMs, have been developed for most of the world. Data have been produced at considerable cost, and there is continuing processes of DEM renewal and improvement. Most terrain analysis are performed using a raster data model. While TIN and other data models have been developed to store and facilitate terrain analysis, raster data structures are more commonly used. Raster datasets facilitate the easy and uniform calculation of slope, aspect, and other important terrain variables. We use the concept of z-values, the height scored in raster arrays, to extract information about terrain, using the magnitudes and patterns of changes in z across the grid. Many terrain analysis functions can be specified by a mathematical operation applied to an appropriate moving window. A subset of commonly used terrain variables include height, which is the elevation above base, slope, which is the rise relative to horizontal distance, aspect, which is downhill direction of the steepest slope, upslope area is the watershed area above a point, flow length is the longest upstream flow path to a point, upslope length is the mean or total upstream flow path length from a point, profile curvature is the curvature parallel to slope direction, plan curvature is curvature perpendicular to slope direction, visibility is the sight obstruction from given viewpoints. Slope and aspect. Slope as a percent equals the rise over the run times 100. Slope as degrees is the inverse tangent of A divided by B. Slope is defined as the change in elevation, or rise, with a change in horizontal position, a run. Slope is often reported in degrees, between 0, which is flat, and 90, which is vertical. The slope is equal to 45 degrees when the rise is equal to the run. The slope in degrees is calculated from the rise and run through the tangent trigonomic function. The tangent of the slope angle is the ratio of the rise over the run. The inverse tangent of a measured rise over a run gives the slope angle. Slope may also be expressed as a percent, calculated by 100 times the rise over the run. A slope of 100% occurs when the rise equals the run. Elevation is often represented by the letter Z in terrain functions. These terrain functions are usually calculated with a symmetrical moving window. A 3x3 cell window is most common. Each cell in the window is assigned a subscript, and the elevation values found at window locations referenced by subscripted z-values. The slope at each center cell is most commonly calculated from the formula slope equals a tan of the square root of dz over dx squared plus dz over dy squared, where s is the slope, a tan is the inverse tangent function, z is elevation, x and y are respective coordinate axes, and dz divided by dx and dz divided by dy are calculated for each cell based on elevation values surrounding a given cell. The symbol dz over dx represents the rise, or change in z, over the run in the x direction. And dz over dy represents the rise over the run in the y direction. A third-order finite approach is a method for calculating dz over dx and dz over dy that differs mainly in the number and weighting it gives to cells in the vicinity of the center cell. The 4 nearest cells are given a higher weight than the corner cells, but data from all 8 nearest cells are used. The method using the 4 nearest cells was among the best for smooth terrain, and the third-order finite difference approach is often among the best when applied to rough terrain. Aspect is used to define the direction water will flow, to estimate the amount of sunlight a site may receive, and to determine what portion of the landscape is visible from any viewing point. The aspect at a point is the steepest downhill direction. The direction is typically reported as an azimuth angle, with 0 in the direction of grid north and the azimuth angle increasing in a clockwise direction. Aspects defined this way take values between 0 and 360 degrees. Flat areas, by definition, have no aspect because there is no downhill direction. As with slope calculations, estimated aspect varies with the methods used. Tests have shown the 4 nearest cell and third-order finite difference methods again yield among the most accurate results. Profile curvature and plan curvature are 2 other local topographic indices that are important in terrain analysis and may be derived from gridded elevation data. Profile and plan curvature are helpful in measuring and predicting soil water content, overland flow, rainfall runoff response in small catchments, and the disruption of vegetation. Profile curvature is an index of the surface shape in the steepest downhill direction. Profile curvature may be envisioned by imagining a vertical plane slicing downward into the Earth's surface, with the plane containing the line of steepest descent, or aspect direction. The surface traces a path along the face of this plane, and the curvature is defined by the shape of this path. Smaller values of profile curvature indicate a concave or bowl-shaped path in the downhill direction, and larger values of profile curvature indicate a convex or peaked shape in the downhill direction. Plan curvature is the profile shape in the local direction of level, at right angle to the steepest direction. This means plan curvature is measured at a right angle to profile curvature. Plan curvature may also be envisioned as a vertical plane slicing into the surface, but with plan curvature, the plane intersects at a 90-degree angle to the direction of the steepest slope. Concave plan curvature values are small or negative for sloping valleys or clefts, while convex plan curvature values at ridge and peak sites are large or positive. These concepts of directional terrain shape may be developed further to identify terrain or morphometric features. These are characteristic terrain elements, including plains, peaks, passes, saddles, channels, ridges, and pits. Hydrologic functions. Digital elevation models are used extensively in hydrologic analysis. Spatial functions are applied to DEMs to yield important information on hydrology. A watershed is an area that contributes flow to a point on the landscape. Watersheds may also be named basins, contributing areas, catchments, drainages, and subbasins or subcatchments. The base of the drainage network is often called a pour point or outlet. Flow direction is used in many hydrologic analysis. Flow directions may be envisioned as all flow from a single cell to a single adjacent cell and stored as compass angles in a raster data layer. Acceptable values are from 0 to 360 if the angle is expressed in degrees azimuth. Alternatively, flow direction can be stored as a number indicating the adjacent cell to which water flows, taking a value from 1 to 8 or some other unique identifier for each adjacent cell. A drainage network is the set of cells through which surface water flows. Drainage networks are also based on the flow direction surface. Streams, creeks, and rivers occur where flow directions converge. Thus, flow direction may be used to produce a map of likely stream location prior to field mapping a stream. Random errors in DEM elevation values often create spurious pits, also known as sinks. Pits are cells that are lower than all other surrounding cells, and they often cause problems when determining flow direction. DEMs must be conditioned to remove erroneous depressions. This involves pit identification, followed by either filling or downcutting downstream cells to remove the pit. Typical steps in a watershed and stream delineation include: 1. Condition the digital elevation model. 2. Determine flow directions. 3. Determine flow accumulations. 4. Determine stream thresholds. 5. Place outlets. And 6. Develop the watershed. The specific catchment area, or SCA, is defined as the total area draining to a point, relative to drainage width. In raster datasets, this is calculated as specific catchment area, or SCA, equals area divided by C, where area is the accumulated surface area upstream from a point, and C is the raster cell dimension. The stream power index, or SPI, is defined as SPI equals SCA times the tangent of B, where B is the slope at a point and SCA is defined as in earlier. SPI is used to identify the potential erosion at a point, which depends both on the upstream area and hence ability to accumulate water, and the local slope, which drives the erosion energy in water flow. Profile plots. Profile plots are another common derivative of elevation data. These plots sample elevation along a linear profile path and display elevation against distance in a graph. Elevation is typically plotted on the y-axis and horizontal distance on the x-axis. These profile plots are helpful in visualizing elevation change, slope, and cumulative travel distance along the specific profile path. Contour lines. Contour lines, or topographic contours, are connected lines of uniform elevation that run at right angles to the local slope. The formula for calculating contour placement between 2 points is d2 equals d1 times ht minus hc divided by ht minus hb. Viewsheds. The viewshed for a point is the collection of areas visible from that point. Shaded relief maps. A shaded relief map, also often referred to as a hillshade map, is a depiction of the brightness of terrain reflections given a terrain surface and sun location. Shaded relief maps are developed from digital elevation data and models of light reflectance. Diffuse light is scattered by the atmosphere and illuminates shaded areas, although the illumination is typically much less than that from direct beam. The brightness of a cell depends on the local incidence angle, the angle between the incoming light ray and the surface normal. The surface normal is defined as a line perpendicular to the local surface. Direct beam sunlight striking the surface at a right angle provides the brightest return, and hence appears light. Calculating a shaded relief surface requires specifying the sun's position, usually via the solar zenith angle, measured from vertical down to the sun's location, and the solar azimuth angle, measured from north clockwise to the sun's position. Local slope and surface azimuth define a surface normal direction. GIS Fundamentals, Section 11, Terrain Analysis, Section Summary. Terrain analysis are commonly performed within the framework of a GIS. These analyses are important because terrain governs where and how much water will accumulate on the landscape, how much sunlight a site receives, and the visibility of human activities. Slope and aspect are two of the most used terrain variables. Both are commonly calculated via trigonometric functions applied in a moving window to a raster DEM. Several kernels have been developed to calculate changes of elevation in x and y directions, and these component gradients are combined to calculate slope and aspect. Profile curvature and plan curvature are two other important terrain analysis functions. These functions measure the relative convexity or concavity in the terrain relative to the downslope direction for profile curvature and cross-slope direction for plan curvature. Terrain analysis are also used to develop and apply hydrologic functions and models. Watershed boundaries, flow directions, flow paths, and drainage networks may all be defined from digital elevation data. Viewsheds are another commonly applied terrain analysis function. Intervisibility may be computed from any location on a DEM. A line of sight may be drawn from any point to any other point, and if there is no intervening terrain, then the 2 points are intervisible. Viewsheds are often used to analyze the visibility of landscape alterations or additions, for example, when siting new roads, power lines, or large buildings. Finally, relief shading is another common use of terrain data. A shaded relief map is among the most effective ways to depict terrain. Terrain shading is often derived from DEMs and depicted on maps.